Okay, everyone, let's start. Really happy to see you all here who survived after the amazing SCC conference, and welcome everyone who just joined for the hackathon. So today we're going to have 3 speakers. We start with Dmitry, CTO of Fluence, and Dmitry is going to tell us about how to build a decentralized backend with Fluence. And after Dmitry, we have Portia from Protocol Labs, and Portia will present IPFS and how to start with IPFS. And after Portia, we have McLean from NewCipher. McLean will tell us about building end-to-end encrypted decentralized application. So please be active, ask questions, and let's start.
Hi. Thank you for coming. My name is Dmitry, and I'm doing engineering at Fluence Labs. What I'm going to talk about today. First, I will tell you about what is Fluence and about the theory and reasons for it to exist. Then I will talk about the DevNet. We have DevNet Live this week. I will tell what is shipped and how it can be used. And finally, in case I'm lucky and Wi-Fi works, in case you will give me a chance to do it by disconnecting from Wi-Fi, I will make a short demo of the DevNet and show several applications. So, what is Fluence and what are the reasons for it to exist? Fluence gives you a wonderful possibility to run applications. These applications are fast and cheap, comparable to cloud computing. They are stateful, like, for example, databases are, and they are developer-friendly, as WebAssembly ecosystem is. So that's pretty familiar for most of us. But also, these applications are decentralized. They are executed in the decentralized environment. They are publicly verifiable, and there is no need to trust any party involved in computations. So Fluence offers a combination of 2 worlds, of conventional worlds with its qualities, and of the decentralized world with all the decentralization benefits. But Fluence is not a blockchain. You can think of Fluence as a network of application-specific blockchains with a shared security layer. And while usually blockchains are used for some kind of financials, usually blockchain data is stored forever, and blockchains take a lot of nodes per chain. All of this for Fluence is not necessary. Blockchains could be small, history could be deleted, and the aim is more generic than just financials. So you could run, for example, decentralized application backends on Fluence or databases, and we have a SQL database deployed on Fluence right now, and REST APIs, and so on. So how could it be possible? How we managed to have all these qualities in Fluence network? The key is the hybrid architecture. So we divided the network in several layers. First, we have a speed layer. Then there is a security layer. These 2 layers belong to Fluence nodes and are running on the Fluence nodes. And also for data availability, we refer to Swarm. And for dispute resolutions, as a final judge, we refer to Ethereum. So let's take a look inside the technology and start with the speed layer. Speed layer consists of real-time clusters with one application for each cluster. Clusters could be really small. It's okay to have a cluster of 4 nodes in a cluster in Fluence, or you could even have a single node cluster, and it also will be working. Client communicates with the cluster directly, and the cluster is responsible for real-time communication, real-time processing. All the data required for the application is stored locally on the same machine where the code is, and the history of transactions is uploaded to Swarm. It's important because we have to enable the access to the data of the cluster from the outside the cluster to perform validation. And validation is done in security layer. Security layer consists of batch validators. Batch validators keep real-time clusters in check. So validators are independent. They are independent from each other, and also they're independent from the real-time clusters. They're stateless, so any node in the network which has enough capabilities can become a validator. And validators are randomly selected, so they are not known in advance. How the validation is performed in network scale. Here we have a chain of blocks which are stored in Swarm. These blocks contain transactions and well, they are built from tendermint blocks from real-time transactions. A part of the history, a history fragment, is selected and assigned to one particular validator. So his duty is to perform verification for all of these transactions. And in case this validator is not the first one, it also verifies the previous validation. It's important to say that the validator never knows if it's the last one in the sequence of validations, so it's quite risky to fake validation job. That's how we motivate them to behave. In order to perform validation, it's necessary not only to have the history fragment, but also the preceding state of the virtual machine. It's also stored in Swarm, and to perform validation, the validator downloads both the history fragment and the previous snapshot from Swarm, then replace transaction history, applying transactions one by one and checking that all the hashes match. And in case no divergence is found, then it uploads the new snapshot back to Swarm. And this enables the possibility to delete, to remove all data from Swarm, and also to perform compaction in a real-time layer, in speed layer, which helps with cost efficiency. So you don't need to store everything forever. Any state transition which is made by real-time cluster might be disputed. And for disputes, we delegate to Ethereum as a final judge. So disputes are resolved by the Fluence smart contract on Ethereum. Ethereum has limitations, I would say limitations in its capabilities. The job to find the mistake must be narrowed down, and to narrow down the divergence in execution traces, we apply verification game algorithm. And of course, the node security deposit is at stake, and that holds both for real-time nodes, where all the nodes participating in the real-time cluster are responsible for the cluster for the computations, and for state transitions and for responses to be correct. And the same holds for validators. So, what's the motivation for all these technical solutions? Main motivations for for the speed layer are cost efficiency and performance, which are in turn are driven by user adoption, because it should be cheap enough and user experience must be good enough to get involved into all this crypto. So real-time workers are stateful, and this really helps with latencies. For example, let's assume that we want to build a decentralized SQL database which is going to perform a query, quite simple query like this. In this case, usually the information is organized in bit trees, in indexes. And to traverse a bit tree index, you have to fetch the tree nodes one by one. And you don't know in advance which ones need to be fetched and which are not. So if you store this index in some decentralized storage like Swarm or Ipfs or something like that, then you have a lot of network round trips before you get result. With Fluence, you can have all the data locally, which is fast. Second, real-time clusters contain only few workers. So real-time BFT consensus is reached fast. Currently, it's about a second to get the result, and probably it's due to the timeouts on the client side. Doesn't matter. But as clusters are small, then they could conspire with each other, and the whole cluster could be captured by adversaries. And this problem could not be solved simply within this layer of fast computations. And that's why we have a security layer. For example, let's imagine that we have 10% of malicious nodes in the network. Let's compare two approaches. One approach is to have the number of nodes in a homogeneous BFT cluster. Another approach is a hybrid verification, like it's done by Fluence. In case we have 7 nodes in a BFT cluster, there is a significant chance to have all the cluster captured. But in case of hybrid verification, if we have the same budget for the computations, but divide this budget between workers, real-time workers, and for paying for validations, we have 2 orders of magnitude better chance to, well, to survive. That's because in case of batch validations, it's enough to have a single honest node to find out the mistake and to have the misbehaving nodes punished. Finally, this design enables speed, security, and cost efficiency in Fluence. Speed is achieved because clients have no need to wait for validation prior to having the results of the transaction. And also, we have just a few workers per cluster, and we store data locally. This helps both with speed and with cost efficiency. And for security, we have eventual validation, and validation penalizes misbehavior. So that's all about the theory for today. And the good news is that we have not only theory, but we could switch to practice, hopefully, because we have a DevNet live. Under the DevNet term, I understand a minimum viable network made for developers. You have seen this slide already. DevNet right now is a speed layer, but it's really implemented. So everything that you can do with Fluence, you can do right now. We have several examples, specific examples of Fluence applications. For example, you can make fair gambling, like the game of dice. We have a tutorial for it and it's deployed. You could have a decentralized database, for example, SQL database, and we have one. It's deployed. You could implement the blockchain search indexes or multiplayer games with low latencies and so on. That's how we decided to separate the main major milestones of the network. At first, we implemented the speed layer, which enables decentralization of applications right ahead. The next milestone is security layer with batch validation. And finally, we will have an incentivization layer, and that will make it the mainnet. While we have no incentivization layer, there could be some problems with applications availability. And to solve this issue for the DevNet period, we have application pinning functionality. It works just like pinning the files in Ipfs, where Ipfs enables decentralization of file storage right ahead, but you have to pin the files if you want to be sure that they won't disappear. And the same holds for Fluence and for decentralization of computations. So you may pin applications to your own nodes for availability guarantees. Here are some important links. I'm not sure they work now, but I will check as I want to have a demo. But there is a dashboard that shows the status of networks and of the applications and of the tendermint chains of the applications. We have the book, the Fluence book, with tutorials and some in-depth insights of the design and of the workflow of applications development. And in case you have any questions regarding theory or applications or I don't know what, please join our Discord. Our development team is always here. That's all for presentation. Let's try to have a demo. And for demo, I will try to switch off Wi-Fi and then switch on, and if all of you disconnected, maybe I will have internet and show you how Fluence works. And just a minute. Maybe it will happen. Well, I suppose it won't happen. Not today. Yep. No internet. I'm sorry. But look at this URL. Wonderful URL. It's easy enough to write on a piece of paper even, and you can type it in your web browser later and see the demo yourself. Hotspot. If anyone have a hotspot to share internet. How should I do it? So let's just imagine that I have shown you the dashboard and clicked on it, and you have seen that everything works, and then you have internet here. Oh, if you give it to me, I will be happy to show you something. Anna, ну да, laptop. Thank you for your support. Wonderful.
Prefer
It, it doesn't matter. I just need to open the website, and it will be a kind of a battle check for our DevNet that it works not only on my laptop.
you can even try the
Could it be mirrored so that I can see what happens? Oh, well, let's call it disaster and switch to questions, please.
but I will
By the way, we have a workshop overnight on the hackathon at 1 a.m. Please all come to us.
If you're still
Let's sleep
awake.
here.
So, any questions? Please get the microphone.
Not the
One
pass.
question. Yes.
Is it?
Hello?
No, it's not. Not this. Not this.
May I ask?
This one.
Should I wait? Should I wait or should I ask?
You could ask.
Okay, I'm asking. So, have I understood you correctly that your use case essentially is a some kind of database cluster, but running not by a single entity, but by collective of entities? They are not trust each other. Is it that use case or it's another one?
I'm really sorry, but the question sounds very complicated to me. Could you?
Okay, I try to understand what is the use case of Fluence. Is it some kind of cluster, database cluster, running by a couple of entities that do not trust each other? Is it that this cluster can be set up in the same in the physical proximity, but it's not like a blockchain, but the runner of the cluster, they are independent and do not trust each other. Is it this use case? Is it some kind of database cluster running by a couple of...
This is the most simple definition of what is Fluence.
Mhm.
Fluence is the network. It's not some entities. It's a network of Fluence nodes which form application-specific blockchains. And these blockchains are running with Tendermint. And these applications are stateful and fast. So you could run any backend on it. Under any backend, I understand really almost any. For example, databases or games with perfect information or blockchain search indexes if you find the way to put the data from blockchains we are planning to do it. Have I answered your question? Have I managed to understand you?
Yeah, most probably.
Thank you. We could have a discussion later about all this.
Hi. Are you competing with Cosmos? Because the first sentence sounded very much like what they're trying to do. What's the difference?
Well, actually, we are trying not to compete with Cosmos, and actually, I don't understand if we do or not. Well, no answer. Sorry, I will figure it out.
And second question, I guess. So you guys have chosen Swarm for the data layer. What was the motivation for doing that? And are you planning to also provide support for like IPFS as the data layer? Thank you very much.
Yep, for this question. In Swarm, wonderful again. I'm not sure I should try. Thanks. So, we want to solve the new problems and bring the new value for the community, and not to do the job of others, which is done much better for by other teams. So in Swarm, there is a theory for guarantees of retrievability with the swarm swindle, I suppose, protocol. And that's the only reason why we depend on Swarm. So we, in the protocol of Fluence, we store all the receipts when we upload data to Swarm, and we rely on these insurances of the data storage of the Swarm layer. The same holds for Ethereum, by the way. That's why we have no another blockchain to make smart contracts better. Any other question? No more questions. Thank you for your attention. Please follow some links and see you on the hackathon. Thanks.
Thank you, Dmitry. So next we have Portia. Nice. Thank you, everybody. Thank you.
Thank you, everyone, for your assistance. Oh, don't clap yet. Wait till the presentation's finished. The jury is still out on this one. So today we're talking about getting started with IPFS. I'll give you some caveats. This is not going to be an especially technical presentation, but it is something at the end of this talk to get you up and running and started using the IPFS stack. So let's begin. Oh, who am I? I don't think it's that important. My name is Portia. I'm part of the community team, and I work for Protocol Labs, and we actually have some other Protocol Labs peeps in the back. Yay! We travel in bunches, so excellent. So let's get to the presentation. What the heck is IPFS? IPFS is interplanetary file storage. Okay, presentation done. Not exactly. Did someone say let's go eat? You guys already had pizza. So this is IPFS. IPFS is, in a word, distributed storage. So let's go over some important facts about IPFS. So IPFS is not an island. It uses libp2p under the hood. It implements the bit swap algorithm, which is very close to BitTorrent. So when I'm talking to people who are not familiar with IPFS, and I talk about the distributed web, their eyes glaze over. But when I mention, hey, remember when you used to share illegal movies? No, IPFS is not about sharing legal movies, but the algorithm bit swap is very close to the algorithm BitTorrent, and I use that as a way to get people at least to think about the architecture of IPFS, even if they're not coming from a technical background. IPFS at this point has two main APIs, which is JavaScript and Go. So if you are a JavaScript developer or a Go developer, you can not only use it, but we're also looking for contributors. And IPLD is the data model behind IPFS. So once again, we're looking under the hood. And IPLD is it's a data model where it links different hashes, like one hash to another. So it's decentralized storage. Data isn't just on a server. Once again, this is important because I think this is important for people outside of ETHCC or outside of our community, because we hear about the controversies of Facebook, the controversies of Google, and the problem, it is ethics, but this is a problem we can also solve with technology. This is a problem where we should not keep all of our data in one proprietary database or data store that we don't have control over. So what we do instead is that we have data in nodes. So we have nodes and we have data in hashes, which are CIDs, that's content identifiers. Why is this important? This is important because if you live in a place like Turkey, or if you live in a place like China, or who knows, even the United States, and we don't know it yet, content can be blocked. Not only do technologists gravitate towards IPFS, but you also have journalists. So you have journalists in places like Turkey, you have journalists in places like Egypt that are using IPFS to create a wiki of sorts. And when you have this system, when you have a CID, this is more stable than using HTTP, which is based on location. Anyone who's had GeoCities or anyone who had GeoCities? Yay. More than I expected. So anyone who had a beloved GeoCities page knows what it means when it goes away. And IPFS is kind of here for you. IPFS is making sure that if GeoCities is gone, your flashing JavaScript or your flashing page with a content identifier will always be there if there's a node solving it. So with data stores, there are different data models. The data model that we're mostly using today, when I mention like Facebook or when I mention Google, is centralized. You also have decentralized, which is IPFS, and distributed. What I like about these different data models, and I talk to people about this all the time, is I think IPFS does two of those well, which is decentralized and distributed. But I tell people that if you just want distributed or you just want decentralized, there are actually other data stores out there. The one that comes to mind is CockroachDB. And oh my God, I see someone raising their hand for CockroachDB. CockroachDB is, I would say it's decentralized. And I think this is important because when you're talking to people about blockchains, different data stores, it's really important for you to make your case on which category you fall in and which problem that you're trying to solve. So why is this important? If you read Gizmodo, there's a great piece called Life Without the Tech Giants, and it's basically about a woman who went a week without using Amazon, Google, Netflix, and I'm forgetting, and I think Facebook. She had a really hard time doing this, and this really shows the problems with our centralized world, is that there are very few options if you want to look at a website, if you want to share data, or if you want an email that's not based on Gmail. These services are very convenient. They have brought us a lot of different value, but the thing is that many of these are monopolies, and IPFS is showing you that there is an alternative to the monopoly of the things. Great. How do I get started building with IPFS? So when I use IPFS, I like to use Truffle. And what I think of IPFS, oops, nope, not demo time yet. So IPFS, I think of this as the new full stack. When I talk to full stack developers about blockchain or about the distributed web, many of them do not know where to start. And I think a good start is showing that Truffle is the framework. And when you think of frameworks, I'm thinking more of like a Ruby on Rails. I'm thinking of a Django. You know what? No value judgments here. I made my career off of Django for 2 or 3 years. But the thing is, when we're thinking about getting people involved in a distributed web, I think it's important for us to have different mindset, to have a mindset or to have a framework that they're used to. So I say instead of using Ruby on Rails, you can use a Truffle. And instead of using a CDN or a data store, you can use an IPFS. So what does this look like in practice? Demo time now. All right. So this is Truffle. I love Truffle. I use it a lot, and I think it's a great way to get started with Ethereum. So when I'm using IPFS and Truffle, like Truffle, I like using Ethereum, which is great, but I don't think Ethereum at this point is good for storage. So after I go to the Drizzle React app, and if you're ever using the Drizzle React native, the best thing to do is for you to actually go to GitHub, because GitHub, they actually have the latest code as opposed to the box that they have on their website. So I take this, I download it, and I install it on my machine, and I get this. So what you're seeing here is the Truffle box. This is everything that I downloaded. And here is, so this is what it looks like. So this is, this can run on Ethereum, and this is actually using IPFS. I will show you how it is using IPFS. If we go into Inspector, and if we go into, give me a moment, Network, refresh. So this right here, which is the CID, which it says failed, unfortunately, is the actual asset that I'm using to serve the asset I'm using over IPFS. So I'm wondering why this has failed, and what I'm going to do is go into my terminal. And when I'm going into my terminal, this is the Truffle part. If you want to get started with the IPFS part, you would go to IPFS, download it, do IPFS init, and then run the daemon. So I should be running the daemon locally. Let's see. Okay, so that's great. This is not working because I am not serving it from my daemon. So I'm going to actually start IPFS so that I can serve that content. Spelling is important. Can you say it again? Make it Greek. I'm not going to change the color now. Can we turn off some of the lights? Would that be better? See it better. Oh, another solution. So we're running the IPFS daemon, and I know it's running because I have Companion. And Companion, if you are using IPFS and you have someone who is not familiar with the command line, they can download the GUI, which is Companion. Companion shows you the gateway. So the gateway here, I'm running the gateway locally, and I'm acting as my own distributed server. I have 4 peers, and I can switch to the GUI. And a GUI will give me more information. A GUI, I can actually add files. But if I do not want to use the GUI, I can just use git add. So what I'm going to do before I show you how to add a file and make it into a CID, let's go back to our Truffle app and see if the asset is there. So here's our CID, and I get a 200. And and I have a favicon over there, and that is using IPFS. But let's say I want to put in a logo. So if I go into my code, So the page that you were looking at is home.js. And here I have an image tag. So in that image tag, instead of using like a regular CDN, I would like to add a hash or add a content ID using IPFS. So what I do is I go into my terminal and I will look for my assets. Give me a moment. Images. And I have 3 images. And so I want to add the architecture diagram. And so I put in IPFS add. And I get a hash. I love the support. Thank you. So I take the hash. I go back into my code, which is home.js, and I need the full link. So the full link of this would be home IPFS, and then my hash. Yay, but not. So that works. So I put this link into home.js, into the source. I take my page, which is here, and IPFS power. So this is a way that you can use IPFS. Oh, thank you. So this is a way that you can use IPFS as a CDN or as a server without using a centralized server. And these are the commands that I put in. I put in IPFS init. That's what you use when you first get started with IPFS, IPFS daemon, and then IPFS add, well, in this case, pretty selfie, and then I get the hash. Let's say that you want someone to use IPFS and they do not know how to use the command line. So what you do is you go to companion, which I already showed you, open Web UI, go into files, and add file. Let's see if we have any images. Let's use a screenshot of the IPFS weekly call. We're open at. Here is our screenshot, and here is our hash. And if we want to add this, we can just go back into the code. We'll change our hash, excuse me. Save it. And nothing. Boom, boom, boom. So let's go back to home. And what we can do is share. So let's use this link. Go back into our source code. See if that works. And voila, there you go. So the point is that we want to create a web where everyone can take advantage of the distributed attributes, and you don't have to be a technologist. You don't have to be someone who's comfortable with the command line, or even if you are comfortable with the command line, we have APIs for you. And let us continue with the presentation. We are finished now. So IPFS and Truffle, we already did our demo. Come hang out with us. If you have any questions, you can go to Discuss. It's pretty active. We're always answering questions. And if you want to help us build the distributed future, then you can contribute. We have Node developers, we have Go developers, and we also are creating packages in Python if you're interested. And if you want to stalk me, I'm pcafe on Twitter, and that is it. Thank you for your patience.
Thank you so much, Portia.
Wait, there's more goodness. There's more goodness. So let's say if you're inspired by this presentation and if you want to help us, we actually have an event called IPFS Camp. IPFS Camp is for builders who want to use IPFS, who want to learn about IPFS. We have dedicated workshops, and this is a chance for people who are using other distributed technologies to learn about IPFS and to learn how they can use it for their current and future projects. And we are in Barcelona this year. So if you want to go to a nice place and learn about IPFS, please join us at IPFS Camp. Okay, now I'm really done.
Sounds amazing. So, first.
Thank you for your presentation. I have two very complex for me questions. First of all, as I correctly understand, any files which you are uploaded to IPFS system will be shared with different nodes of IPFS. So my question is how I can delete this file from any nodes of IPFS?
Well, the thing is, it will be, if you're not pinning it, the cache will be cleared and it will be gone, if I'm not mistaken.
And the second, are there any ready-to-use solutions to implement some politics of sharing files between nodes?
Can you say it again, please?
I have a case. For example, I want to download this file, but I want to share this file exactly which list of nodes of IPFS. Are there any ready-to-use solutions of this?
Well, there's libp2p under the hood, and libp2p has an experimental feature where we have private nodes. We need more people to work on it, so that's something, that's a use case that you're interested in. Please contribute.
Okay, thank you.
Actually, if someone next.
Could you please elaborate more on what happened to the file you uploaded? Like, what happened under the hood? How is it distributed? What if you disconnected from the web? Did it still exist? Like, what happened there?
Well, great question, because when I originally was showing you the app, I was not running the node. So the node has the different hashes, and if you are not running a node, then you will not have access to the CID or the content that you uploaded on IPFS.
But is it only hashes, like the content itself is distributed or not? Or does it exist on my node only?
It only exists on one node, but you have access to that node if your node is up and running.
So how is it distributed?
It's distributed because it has a content. If you know the content address and you know what the node is, then you have access to it. So it's more distributed in terms of it's there, and if you know what the node is, what the content ID is, then you have access to it.
Okay.
We can talk after, and I can give you more of a detailed answer.
Can we switch on the lights? Anybody? Could you switch on the Thank you.
Hi, thanks for the talk. Could you elaborate on the pricing structure and what's planned for that? The pricing? Okay, thanks.
Is the microphone okay? Yeah. Let's switch the microphone.
Thank you.
Okay. The last question.
So if I understand, the image you uploaded is only in one node somewhere on the network, and we don't need to know where it is, right? It's not on my node, it's somewhere on the network.
If you're looking for a particular content, you would
Yeah.
need to know the content
Yeah.
ID.
The content ID. So there is no redundancy. I mean, there is no guarantee that my content will stay there if this very node goes down one day.
There, in terms of persistence, no, there is no persistence. However, if you're using IPFS cluster, you can pin your content, and that would guarantee that it's on your node. Thank you.
Very inspiring presentation. Thank you. And next we have McLean. He's CEO of NewCipher, the founder.
Hi, everyone. My name is McLean Wilkeson. I am one of the co-founders of a project called NewCipher. And NewCipher is the data privacy layer for Ethereum and Web3 and decentralized applications. Our purpose for existing as a company is to build the tools and the infrastructure that makes it easy for all of you as developers to build privacy-preserving applications and privacy-preserving protocols. We really work on two core pieces of technology. The first is our threshold proxy re-encryption network, and that's most of what I'll focus on today. And then the other is sort of longer-term R&D that we do in the field of lattice cryptography and specifically fully homomorphic encryption. But the focus of this talk is going to be on the NewCipher network, which uses exclusively proxy re-encryption for the moment. And it's basically a decentralized access control or key management service that gives you a way to enforce access conditions in your decentralized application. So a simple example would be if you're building some sort of healthcare application on top of Ethereum and IPFS, you could store, let's say, patient medical records on IPFS or Swarm, have those be private and encrypted, but still shareable with, let's say, your hospital or your doctor. And so the obvious question is, like, why not just use traditional public key or traditional asymmetric cryptography to achieve this? It's very well understood. If we take public key cryptography, for example, you have Alice and Bob, this sort of traditional cryptography narrative. Alice has some secret message that she wants to share with Bob. All she has to do is encrypt with Bob's public key, shoot it across the network. He can use that. He can use his own private key to decrypt that data. It's very well understood, very easy, very secure. Where it gets a little bit murkier is if we extend this into the context of an application. And for web servers today, or web applications today, almost all of the web services we use, like Dropbox, Amazon, Google, Gmail, are predicated on this idea of server-side decryption. Obviously, if Alice was to upload encrypted data to Dropbox, there's no way for Dropbox to share that data on to some other recipient. And given that most applications are multi-user, this sort of sharing requirement is pretty important. So basically what that means is, all these central service providers have to decrypt the data server-side. And maybe that's okay. Maybe we trust Facebook, maybe not. Maybe we trust Google, et cetera. But we certainly don't trust some of the people that may be trying to break in to those central services. And if we take it sort of the next logical step into what we're all working on in a decentralized world, this idea of server-side decryption is a complete non-starter because the nodes that we're decrypting data on could literally be controlled or run by the very people that we're trying to keep our data private from. You could have an Ethereum node or an IPFS node or a Swarm node or anything like that under the control of a malicious nation state or some sort of black hat hacker. And so if we imagine kind of what it would look like to build some sort of network predicated on just vanilla asymmetric public key cryptography, that would basically mean that every single node is going to have access to your plaintext data. So any single node can deny you access to that data. Any single node can share that data with people maybe you don't want them to share it with. So if we took just traditional public key cryptography a step further, some of you might be familiar with this idea of Shamir's secret sharing, where we can actually split a private key up into a bunch of different shares. We could imagine perhaps building some sort of network using Shamir's secret sharing where different nodes in the network have a different key share. Obviously, this is better than every single node having the whole private key, but it's still very susceptible to collusion. Let's say you split that private key up into 3 shares. If those 3 nodes that have each of those shares can identify each other, they can just sort of decrypt your data and share it on without your consent. And so we need some way to sort of close this loop. So the data is always encrypted from the second it leaves Alice's premises to the second it gets to someone that she explicitly shares her data with. And at NuCypher, we're using something called Proxy re-encryption to achieve this. So what Proxy re-encryption allows us to do is it allows Alice to allow some untrusted proxy to re-encrypt or transform data that's originally encrypted under her key into being encrypted under Bob or Charlie or Dave or Evan's key. And the magic of proxy re-encryption is that this re-encryption happens without ever decrypting in the middle. So the proxy only sees data that's encrypted for Alice, does the re-encryption, it only sees data that's encrypted for whoever the recipient is. So the proxy never sees the plaintext data. Whatever storage layer Alice is using to persist the data never sees the plaintext data either. And just sort of how to illustrate by way of example, let's say this is Alice. She has a bunch of sensitive financial data, in this case, let's say in Excel. She wants to upload that data to some remote storage. It could be IPFS or Swarm or Amazon S3, it doesn't matter. She'll encrypt that data on her client. She'll upload it somewhere. At this point, she is the only one who has access to that data. She's the only one with a private key. If Bob tries to use his key to access that data, it's going to fail. There's no way for him to decrypt it. But let's say we fast forward a little bit and Alice decides actually she does want Bob to have access to that data. What she can do is create something called a re-encryption key. And a re-encryption key has 2 inputs. One is her private key and the other is Bob or the recipient's public key. So once she's created this re-encryption key, which she'll do on her client, there's no way to decompose it into the 2 inputs, so there's no way to get the private key back out. She can give this private key, or this re-encryption key to a proxy in the NuCypher network, and the proxy can use that re-encryption key to re-encrypt or re-key the data that was originally encrypted under her key into being encrypted under Bob's key. And generally, nodes in the NuCypher network are sort of compensated for that work. So once that re-encryption happens, Bob can take that re-encrypted ciphertext and use his own private key to actually decrypt the data. So this has a bunch of nice properties. Obviously, we never expose plain text to anyone other than Alice and Bob. Alice and Bob never have to share their private keys either. So that gets us pretty far. It's a lot better than traditional asymmetric cryptography for this sort of decentralized access control network. It's a lot better than Shamir secret sharing. But we still have sort of one problem with just vanilla proxy re-encryption. And that is that even though none of the nodes can actually see the data, if you just have one re-encryption key with one node, and that node, let's say, goes offline for whatever reason, maybe it just loses power or something happens, maybe it's actively denying service, there's no way for Bob, the recipient, to actually get the data re-encrypted for him. So what we can do, we've actually created a threshold scheme for proxy re-encryption, and it's in principle very similar to Samir secret sharing, except we actually split the re-encryption key up into a bunch of shares. So in this case, we'll split it up into 5 different shares. We'll issue those 5 shares to 5 different nodes in the NuCypher network. And as long as some threshold number of those shares and those nodes are active and available, then the re-encryption will be successful and it will work. So we add a bunch of sort of redundancy into the network. We make it harder for, let's say, a recipient to collude with a node to circumvent any conditions around sharing that Alice may have applied to the policy. Oops. And so that's basically what NuCypher, the network, is. It's a sort of network of these proxy re-encryption nodes that are taking re-encryption key shares, applying any conditions that Alice may want on top of those shares, and then granting access to Bob if he's a valid recipient. So we kind of, you may have noticed there's a couple different, or mainly one additional character that we introduced to the sort of traditional cryptographic Alice and Bob narrative. And that primary character is what we call Ursula. So we just call the proxy nodes in the NuCypher network this Ursula character who's responsible for doing the re-encryption. And we actually use these characters in our code. So if you're writing an application with NewCipher, you'll create classes, Alice, Bob, Ursula. Well, not Ursula, unless you're running a node. And then we also, to make sort of application development a bit easier to reason about, we split Alice into 2 characters. So Alice, the ultimate data owner or the policy owner who decides who has access to data, and then we call the actual data sources Enrico. And the reason why we do this is, let's say I'm an Alice. I could have many different data sources. Let's say my watch, my email, that are producing different data streams. And it's just a bit easier to build applications sometimes. Although very often Alice and Enrico will just be the same character. So if you want to be one of these Ursula nodes in the NewCipher network, we have a native token that you have to stake as a kind of bond or collateral. So it's a work token that we use basically to allocate re-encryption work. We use it to coordinate the network. So let's say you staked 5% of the NewCipher tokens, you'll get proportionately 5% of the work. If you do that work correctly, you'll get 5% of the rewards. And we also use it to ensure that nodes behave correctly. So if for whatever reason you're staking as an Ursula node and you misbehave, instead of properly re-encrypting, you just maliciously give Bob just random gibberish, you would get slashed for that. So we have a way to sort of cryptographically prove the correctness of re-encryptions. So now I'll sort of jump into kind of a demo to kind of illustrate how this all works. We have this heartbeat demo that I think does a pretty good job of kind of very explicitly delineating all these different characters in the network. So we have, in this case, Alice, who is the data or the policy owner. We have an Enrico, which is this heart monitor that's producing data on Alice's behalf and encrypting under Alice's key. And we have a Dr. Bob, who Alice will decide to share data with. And we also have the NewCipher network, which consists of a bunch of these Ursula nodes. One of the nice things about the NewCipher network is we're totally agnostic as to the storage layer that you use. So you can use IPFS, you can use Swarm, you can use Arweave, you can use Amazon S3. We like all of them. Well, maybe not S3 so much, but that's your choice. And for the purposes of the demo, we're just going to save the data locally so that we don't have to wrangle with the Wi-Fi and all of that. I'll make this a little bit bigger. Okay, so what I'm going to do first is I'm going to sort of spin up a network of Ursulas locally on my machine. So the way that will work is I'll run this run lonely demo Ursula script. That will give us our first proxy node. We'll give that a few seconds to spin up. We have code names for all the proxy nodes in the network. In this case, it's this dark slated blue code name. So we've got our first node up, and then we will add a couple more friends so that we have a full network. So we'll run this this fleet script. I think that'll add 5 or 6 more proxy nodes. And so we should, what will happen is all these new proxy nodes will basically connect to this initial Ursula. They'll learn about her, she'll learn about them. So we can see a bunch of these new nodes. If we flip back to the terminal where the first Ursula is running, we should see that she's also learned about all of these new nodes. So now we've got a network of Ursulas, just obviously running here locally on my machine. And that network of Ursulas is available for us to issue access policies to. So we'll open this alicia.py file, and we'll look at how we sort of configure and build an Ursula. So we'll just try to grab an Alice from disk if there's one there. If not, then we will configure a new one. One of the things to note is I have this federated only flag. Basically what this means is because I'm running this network of proxy nodes locally on my machine. There's no blockchain right now in this demo. So it's basically just acting off a whitelist of nodes as opposed to selecting nodes proportional to their stake. So we've initialized this Ursula. We'll connect her to the network. We have this start learning loop, which basically is how Alice and also the Ursulas learn about the other Ursulas in the network. And then we have this concept of labels. So an Alice might have a bunch of different data sets. So she could have her heart monitor data that she wants to share with Dr. Bob. She could have her social media accounts, Gmail, text messages, whatever. She doesn't want to give Bob access to everything. She just wants to give access to exclusively this heart data. So we'll create a label for that, and that sort of specifies what data Bob will have access to. Then we'll generate a bunch of just dummy heart data for the purposes of the demo. And then to create this re-encryption key, remember we need Alice's private key, which obviously Alice has. We also need Bob's public key. So we'll just assume there's some side channel. Maybe she went to the doctor's office, got his public key there or something. We'll initialize this Bob character that she's going to share data with. And then we're also going to attach a couple different policies or conditions to the sharing policy. So one is going to be sort of an end time for the sharing policy. She doesn't want to give Bob access forever. She just wants to give him access for 1 week. And we're also going to set these threshold M of n values. So these are basically the numbers that we split the re-encryption key up into. So n is the number of shares. We'll split it into 3 shares. We'll require at least 2 of those shares for the re-encryption to happen. So M of n are 2 and 3. And then Alice will take all those inputs and grant this policy and issue it out to the network. And assuming that is successful, the network will be living out across these different nodes in the new Cypher network, and Bob should be able to request access to the data. So we will try running that script. Hopefully everything will work. If it does, we'll just get this print out of done in the terminal. So you can see that similar to how the Ursula nodes learned about each other, Alice is also going to learn about a bunch of these nodes as well, or at least 3 of them, because she needs to send out 3 key shares. And so it looked like everything worked. So now we have this policy living out in the new Cypher network. And now we'll fast forward, let's say a few days. Bob decides, okay, he wants to analyze this heart data. So we'll look at the script for him. I'll skip some of the setup stuff. But similar to how we sort of initialized Ursula, we'll create this Bob character. He's also running in federated only mode. What he's going to do is he's going to fetch the encrypted data from storage. So that could be IPFS, it could be Swarm, it could be whatever, but he'll first fetch it. Obviously, it's going to be encrypted under Alice's key, so he has no way to actually read the data. He's going to figure out the label for that data, and then he's going to join that policy using the label and Alice's signing key so that he can verify that the data actually came from Alice. And what he's going to do is he's going to take the chunks of those encrypted data that's under Alice's key and request the new Cypher network to actually re-encrypt or transform the data so that it's actually, from then on, encrypted under his key. So that'll be sort of this little chunk of code here. Assuming that that policy that we successfully issued is out there in the new Cypher network and all the conditions are valid, the Ursula nodes will re-encrypt that policy for him, return him what should be at that point be data encrypted under his key. He'll be able to decrypt, and we'll try printing that out just to see if it all works. And if we run that script, we can see that it does. So it's printing out all these heart data points as they come in, and Bob has access to the data. one thing that's not in the demo but is possible to do with NewCypher is if Alice, let's say she switches healthcare providers, she goes to a different hospital or a new doctor, she can revoke Bob's access from the data in storage. Obviously, if he's already fetched it and downloaded it and decrypted it, there's nothing she can do at that point, but she can at least prevent him from fetching it from storage in the future and just issue a new sharing policy to her new doctor. Okay, so where are we now? Right now, we have a couple different testnets that are available for people to either build applications against. So we have a DevNet, and we also have a staking testnet. So this is the information for the staking testnet. If you go to our docs.newcypher.com, there's sort of instructions on how to initialize an Ursula node and join the network that way. You'd need to use this Uamuamua network domain and this initial seed node, which is the URI of sort of the teacher Ursula who you first connect to. And then we have a dedicated DevNet as well, which is more stable. We run all the nodes as opposed to random people. So it just, if you're building a DApp or some sort of application, we'd recommend to build against the DevNet and not the staking testnet, although you can. It'll just be a little bit more stable, and we sort of guarantee node uptime and things like that. I'll also touch on, just to wrap up, some of the longer term research we're doing around FHE. And fully homomorphic encryption, for those of you not familiar with it already, is this idea that you can perform arbitrary computation on encrypted data. So in the same way that we can run some function or apply some function against plaintext data, get a result in plaintext, homomorphic encryption is this idea that we can take encrypted data, apply some function to it, and get an encrypted result. We're primarily interested in sort of exploring ways to apply this to smart contracts. So looking at ways to build things like, secret token sales or auctions, things like that. Some of the work that we've done so far, we've published. So this is a open source library, new FHE, that's on our GitHub. We use GPUs to accelerate some of the existing FHE schemes, namely this TFHE scheme. And GPUs got us about 100x performance over the existing benchmarks. So right now, this is the fastest FHE library that we're aware of. We actually used it at ETH Berlin, I guess about 5 or 6 months ago at this point, to execute the first ever fully homomorphic smart contract as a kind of POC. And we love for more people to sort of build cool stuff with this and help us sort of push this, this research forward. We're also going to be around this weekend, of course. If any of you are going to ETH Paris for the hackathon, we'd love to see you build something with either NewCypher Network or new FHE. If you can't make it to the hackathon this weekend, we're also running, starting the day after the ETH Paris hackathon, an online hackathon with CoinList. So that will last about a month and totally virtual, so you can work on it from home or wherever in the world you are. I'd love to have a lot of you join that as well. More information, if you're interested in sort of diving deeper into either the FHE stuff or the proxy re-encryption stuff that I can cover in the talk today. We have docs. The core proxy re-encryption network is just on our GitHub. In the NewCypher repo, the threshold proxy re-encryption scheme, it was called Umbrel, and that's also on our GitHub. New FHE is on our GitHub. All of our development discussions happen in public. We'd love to engage with you there if you're interested in building something with NewCypher or contributing to NewCypher. Just hop into our Discord, and generally someone's always around. Thanks very much, and happy to answer any questions.
Thank you, McLean. Would you have workshop also at the?
We will. I think it's at 9:30 tonight, I believe.
Hi, thank you for the presentation. Could you please share a code of your example from this presentation? Share code of demo.
Oh, yeah. So all of this, well, I don't have Wi-Fi right now. But if you go to this repo here, so just go to newcypher.dev/newcypher or github.com/newcypher/newcypher. It's in the examples folder. And then we have these Ursula scripts to spin up local nodes. And then the heartbeat demo is in this heartbeat demo folder.
Okay, thank you.
Thanks for the presentation. Can you talk a bit about like the history of proxy re-encryption schemes? Like, have they been around for a while, or have you guys like done any actual work in like developing them or tooling them to your needs?
Yep. So we did not invent proxy re-encryption. The first paper was written, I believe, in 1998, so about 20 years ago. One of our advisors, Giuseppe Atteniese, was actually one of the sort of original authors of one of the original schemes way back then. But all of the previous proxy encryption schemes have been more sort of research-oriented implementations or academic implementations. As far as we know, Umbrella is the first sort of commercial or production-ready implementation of proxy encryption. It's also different in the sense that it's the first threshold scheme. So all the other schemes had basically one node, one re-encryption key, and our cryptographer basically created this threshold scheme specifically for the new cipher network. But you can, of course, use it as a library for other things as well.
Hey, thanks a lot. You briefly touched on the idea of the token and how the staking the token is sort of like the factor on if you get selected to be a validator or not. Is there any other factor in that, or is it just the stake size? That's the only thing that determines if you're going to be selected.
Yep. So right now, it's just stakes proportional to stake. Nothing's finalized, obviously, until sort of mainnet launch. But yeah, right now you get basically sampled based off of your proportion of stake that you have relative to the rest of the nodes in the network.
Thanks.
Hi. So I have a question about performance. For example, what do you have you done any calculations, as in, for example, the computation costs on 1 gigabyte of data of proxy encryption with a 2 out of 3 scheme? I'm assuming goes up if you want like a larger amount, like larger threshold.
Mm-hmm. Yeah. So the main bottleneck is just network latency. So re-encryption itself is just an elliptic curve function, so it's very fast, almost trivial. And it actually, I didn't really cover it in the presentation, but it doesn't depend on the size of the data, because what's actually happening is you would encrypt. Generally, it's like similar to PGP, if you're familiar with how that works. You encrypt the bulk data with a symmetric key. So it doesn't matter if it's megabytes or gigabytes or terabytes. And then you encrypt that symmetric key with the asymmetric cryptography. Then we do the re-encryption on that encrypted symmetric key. So it's really a function of network overhead. And so basically, as you increase the M of n, or the threshold, basically that would have the biggest impact on performance. But the nice thing is that it's just one trip to each of the nodes. So it's not like some like MPC protocol where you've got to have constant communication back and forth. But network overhead is the primary bottleneck.
Okay. Do you expect, like, if it's so easy to do, then maybe there won't be so much profit opportunity for the node, or?
Sure. So it's not. So the node requirement isn't computationally heavy. It's not like you don't have to run a GPU or anything like that. It's more about availability. So it's very important that the nodes are sort of always online. They're available to service a policy when some recipient requests it. They're also, we also rely on the nodes basically to enforce conditions. So you're getting paid for that. So let's say Alice doesn't want to just share Bob her data immediately. She wants to wait a certain period of time, or she wants to share the data only after he's paid like 5 ETH or something to her address. So the nodes are compensated for availability and enforcing these conditions.
And I guess that's the last two questions, is how do you enforce the time constraint? Like after 1 week, the nodes are not allowed to share it with Bob. How does that work? Because unless I'm mistaken, it's very hard to do like time-based encryption or time-based cryptography. And the second question was, do you use Ethereum or do you run your own blockchain? What's the execution layer?
Yep. So this is a good point on how we enforce certain conditions. So there are certain things that we can sort of prove cryptographically. And one of those is if you ask the node to re-encrypt some data for you, and instead of doing it, they just give you random gibberish, you can basically submit a cryptographic proof that the re-encryption was wrong, and that node will get slashed. So that's actually quite easy to police. There's no way to cryptographically prove the access has been revoked. So basically that's where the threshold scheme comes in. We're kind of assuming that at least, if we have, let's say, a 3 of 5 threshold number, at least 3 of the nodes, are going to properly revoke data. but the guarantees there are a little bit weaker, certainly, or a lot weaker because they're not cryptographically enforced. The other way for a node to misbehave is if it goes offline. So right now, the assumption is, or our working assumption is, we're not going to slash nodes for going offline, because even though we can know if a node has gone offline, we can't really know why that node has gone offline. DDoSes are basically free at this point, so we don't really want to slash people through no fault of their own. They're just getting attacked. So I think what we'll do there is we basically, if you go offline, you just don't get rewarded for the period that you're offline. And when you originally stake the token, in order to run a node, you have to lock it for a period of time. So you basically, the unlock countdown would stop. Oh, yeah, so we run on top of Ethereum. The new Cypher token is an ERC20 token. It's just a staking work token, so it does everything that we need it to do.
Yeah, how would new Cypher work if Alice wants to share a secret message not with Bob, but with a group of people? And how would this work if one of the members of the group leaves and is not allowed anymore to decipher the text?
Yep. So there are a couple ways to do that. You could have like a group key, maybe, where everyone's part of a group that shares a key, or you could have like a bunch of derived keys for each of the people in the group. If someone leaves, you just revoke their particular sort of leaf in that tree of keys, or you could just issue different re-encryption keys for each of those people in the group.